In November of 1930, workers at the Canadian Pacific Railway's Angus shops in Montreal bolted the last steel plate onto something unprecedented, number 8000. A locomotive unlike anything Canada had ever built, unlike anything most of the world had ever seen. It weighed more than 400 tons fully loaded. It stretched over 90 feet from pilot to tender. It had the same massive 210 four-wheel arrangement as the CPR's legendary Selkirk locomotives, those titans of the Rocky and Selkirk mountains that were, at that very moment, hauling passengers and freight through some of the most punishing terrain on Earth. But 8000 was different, profoundly different. Buried inside its boiler shell were not one, not two, but 3 separate pressure systems. 3 boilers stacked and nested like Russian dolls, each operating at pressures that would make conventional locomotive engineers nervous. The innermost circuit, sealed, filled with distilled water, ran at 1,250 pounds per square inch. The next layer, 850 psi. The outermost, a comparatively tame 250. This was the Schmidt high-pressure system, a German invention that promised to revolutionize steam locomotion. A closed, ultra-high-pressure circuit transferring heat to a high-pressure circuit, which exhausted into a low-pressure circuit. Triple expansion, maximum thermal efficiency. On paper, it was brilliant. In practice, it was about to become one of Canadian railroading's most ambitious failures. The man behind 8000 was Henry Blaine Bowen, CPR's Chief of Motive Power. Bowen was a steam man to his core, a British-born engineer who immigrated to Canada and rose through the ranks to command the design and acquisition of every locomotive that rolled on CPR rails. He believed in steam with the fervor of a true believer, and he believed that high-pressure technology could squeeze every last drop of efficiency from the dying art of steam locomotion. In 1930, that belief still seemed reasonable. Diesel-electric locomotives existed, but they were experimental curiosities. Steam ruled. And steam, Bowen was convinced, could still evolve, and the Selkirks were proof of that evolution. Built starting in 1929, these 210-4 behemoths were the largest steam locomotives in the British Empire. They could haul 12-car passenger trains up 2.2% grades through the Connaught Tunnel without slipping a wheel. They pulled freight loads that would have required helpers on any other line. Engineers described them with a mixture of awe and affection, machines that didn't bark like overtaxed locomotives, but chuffed with an almost casual power, as if the mountain grades were nothing more than gentle slopes. But they consumed fuel, massive quantities of fuel, oil, and water. The math was brutal. Every run between Calgary and Revelstoke meant thousands of gallons burned, thousands more in maintenance, and a constant hungry demand for resources that ate into profit margins. Bowen saw 8000 as the solution. If the Schmidt system lived up to its promises, and tests in Europe suggested it might, 8000 could deliver the same power as a Selkirk while consuming 25% less fuel, 25%. In an industry where margins were measured in fractions, that was revolutionary. So, CPR invested. Nearly $300,000, an astronomical sum in 1930 equivalent to millions today, went into building number 8000 at the Angus shops. German patents were licensed. Water tube boilers were fabricated to tolerances far beyond anything CPR had attempted. A third cylinder was mounted in the center of the frame, driven by high-pressure steam, its exhaust mixing with low-pressure steam to feed the 2 outer cylinders. It was the only 3-cylinder locomotive ever built in Canada, a mechanical symphony of complexity. In April 1931, 8000 was rolled out for publicity photographs at Montreal's Windsor Station. The images are striking. The locomotive gleamed under the station lights, its streamlined casing hinting at modernity, its sheer bulk dwarfing the crowd gathered around it. In one photo, an English Austin automobile sat beside the smoke box. You could fit the entire car inside that smoke box and still have room to spare. The test runs began in the spring of 1931. CPR chose the Winchester subdivision between Montreal and Smiths Falls, Ontario, a 124-mile stretch of relatively flat track through the St. Lawrence and Ottawa River valleys. It was perfect for break-in runs, close to the Angus shops, close to the Montreal Locomotive works, close to support if anything went wrong. The first train was light, 70 empty cars, 2,476 tons trailing behind. The dynamometer car, CPR's mobile laboratory for measuring locomotive performance, was coupled in, along with the mandatory caboose. Engineers watched gauges, firemen monitored pressure, executives held their breath, and 8,000 performed. The closed circuit boiler held steady in the 1-200 psi range, sometimes dropping to 1-25, sometimes spiking to 1-450. The high-pressure circuit averaged in the mid-700s. The low-pressure boiler fluctuated between 155 and 230 psi, a wider range than ideal, suggesting that coordinating three pressure systems was more art than science. But the locomotive moved, it pulled, and when the numbers were tallied, the fuel consumption was staggering in the best possible way. 1,251 imperial gallons of bunker oil and 12,150 gallons of water for the entire run. Compared to a conventional Selkirk running the same train on the same track, 8,000 showed nearly 25% fuel savings. The German promises were real. Henry Bowen must have felt vindicated. This was the future. This was how steam would survive, evolve, compete with the diesel-electric upstarts that were beginning to prowl the fringes of North American railroading. But there was a problem. Actually, there were several problems, they just hadn't shown up yet. Summer turned to fall. More test runs, more data. The engineers filing reports noted that maintaining consistent pressure across three systems required constant attention. The fireman couldn't just shovel coal or adjust oil flow. He had to think in three dimensions, balancing circuits that wanted to drift out of equilibrium. It was exhausting. It demanded skill beyond what most crews possessed. And then there was maintenance. After each run, when 8,000 rolled into the shop, mechanics faced a locomotive that was fundamentally different from anything they'd serviced before. Water tube boilers instead of fire tube, triple pressure systems, sealed circuits that couldn't be easily inspected, specialized gaskets and fittings. Every repair took longer, every part cost more. Still, Bowen pushed forward. The mountain service awaited. The whole point of 8,000 was to prove itself in the Rockies and Selkirks, where fuel economy mattered most, where a 25% reduction in consumption could transform the economics of mountain railroading. Sometime in late 1931 or early 1932, the exact date lost to incomplete records, 8,000 was sent west. Not to the Calgary Revelstoke run where the Selkirks reigned, but to Field and Revelstoke, deep in the heart of British Columbia's most unforgiving grades. This was the crucible, this was where legends were made. We don't have detailed accounts of 8,000's mountain service, no engineers' logs have survived, no maintenance reports, no dynamometer car data from those western runs. What we have are fragments, hints, silences that speak louder than records ever could. What we know is this: 8,000 did not replace the Selkirks. The promised fleet of high-pressure locomotives, the ones that would have followed if 8,000 proved successful, never materialized. Production orders were never placed. By the mid-1930s, the experiment was quietly shelved. High maintenance costs, the official line would later state, offset the fuel savings. But that single sentence conceals a world of operational reality. Imagine, you're a locomotive engineer in 1932 assigned to 8,000 for a westbound freight run out of Field. The sun hasn't risen yet. You climb into the cab, and instead of the familiar gauges and controls you've known your entire career, you're confronted with a dashboard that looks like it belongs in a power station, 3 pressure systems to monitor, 3 sets of steam flows to balance. One mistake, One moment of inattention, and you could lose coordination between the circuits, lose steam, lose the train on a mountain grade. And if something breaks, when something breaks, because everything eventually breaks on a mountain railroad, you're looking at delays measured in days, not hours. Specialized parts shipped from Montreal. Mechanics brought in from Calgary because the local shops don't have anyone trained on Schmidt systems. Trains backed up behind you, schedules collapsing, costs mounting. The math that looked so promising in 1931 started looking different by 1933. Yes, 8,000 burned less fuel. But fuel was cheap. Labor wasn't. Downtime wasn't. Complexity cost money in ways that no fuel savings could offset, especially not in the depression-ravaged economy of the early 1930s. And there was another factor, quieter but just as deadly: crew confidence. Other countries had experimented with Schmidt high-pressure locomotives. France built one. So did Britain, the infamous LMS 6399 Fury, which suffered a catastrophic tube failure in its closed-circuit boiler, scalding a crew member to death. Germany's Locomotive showed promise but never entered regular production. Across the Atlantic, American railroads were conducting their own high-pressure experiments, and they were all reaching the same conclusion. The technology was too complex, too fragile, too demanding for everyday service. Engineers heard these stories. They knew that buried inside 8000's boiler was a sealed circuit running at pressures that could turn water into a weapon. Yes, CPR reported no tube failures. Yes, the safety systems worked. But the psychological weight of working with such extreme pressures day after day on mountain grades where a single failure could mean disaster, that weight was real. By 1936, possibly 1937, number 8000 was withdrawn from service. There's no ceremony recorded, no formal retirement. One day, it was a working locomotive. The next, it was yard storage. And then sometime in the late 1930s, it was scrapped, cut up for salvage metal. The water tube boilers, the triple pressure systems, the German technology that cost $300,000 to build, all of it reduced to scrap value, melted down, erased. Henry Bowen remained CPR's chief of motive power until 1948, nearly 2 decades after 8000's failure. He never built another high-pressure locomotive. In 1938, he ordered 10 more Selkirks, conventional Selkirks, designated T1B class, with higher boiler pressure than the originals, but nothing exotic, nothing revolutionary, just proven, reliable, maintainable steam power. And in 1949, in what would be Bowen's last act as Chief of Motive Power, CPR took delivery of 6 final Selkirks, the T1C class. They were the last standard-gauge steam locomotives built in Canada for a Canadian railway. By then, diesels were already working the mountain grades. The writing was on every wall. Within a decade, every Selkirk would be retired, replaced by diesel-electric units that didn't need water, didn't need coal or oil, didn't need the armies of specialized labor that steam demanded. 8000 had promised to save steam. Instead, it became a footnote, a curiosity, a what-if, that enthusiasts discover when digging through obscure railway histories. But here's what makes 8000's story worth remembering. It wasn't a failure of engineering. The technology worked. The fuel savings were real. On paper, everything about the Schmidt system made sense. What failed was the gap between theoretical efficiency and operational reality. The distance between a locomotive that works in ideal conditions and one that can survive the grinding, unforgiving demands of daily service on a mountain railroad. It's a pattern we see repeated across industrial history. Brilliant ideas that fail not because they're wrong, but because they're too right, too perfect, too demanding, too unwilling to compromise with the messy realities of the real world. 8000 needed perfect water quality, perfect maintenance, perfect crews, perfect conditions. The mountains of British Columbia offered none of those things. The Selkirks, by contrast, were gloriously imperfect. They consumed more fuel, yes, but they could be maintained by ordinary shop crews. They could be operated by engineers with conventional training. They could take a beating and keep running. They were machines built for the world as it is, not as engineers wished it could be. Today, 2 Selkirks survive. Number 59321 sits at Heritage Park in Calgary, its paint fading, its Tuscan red panels barely visible beneath decades of weathering. Number 59335, the very last Selkirk, the final steam locomotive CPR ever bought new, resides at Exparail in Saint-Constant, Quebec, preserved as a monument to the end of an era. Number 8000 exists nowhere. No museum saved it. No Railway Historical Society fought for its preservation. When it was cut up for scrap, no one thought it was worth saving. At the time, it must have seemed like just another failed experiment, another expensive lesson in the limits of ambition, but maybe that's what makes its absence so haunting. We preserve the successes, the locomotives that worked, the machines that fulfilled their promises. We rarely preserve the failures, the experiments that taught us what doesn't work, and so we lose the lessons. We forget the roads not taken, the futures that almost were. What if Bowen had been given more time, more resources, more locomotives to refine the design? What if the Depression hadn't squeezed every railway's budget to the breaking point? What if crew training had been better, maintenance protocols more sophisticated, parts supply more reliable? Could high-pressure steam have evolved into something practical, something that actually saved the steam locomotive from diesel-electric obsolescence? We'll never know. History doesn't offer do-overs, doesn't let us run the experiment again with different variables. We only get the outcomes we got and the questions those outcomes leave behind. Number 8000 was supposed to be the future. Instead, it became a ghost, the forgotten Canadian giant that proved you could build something technically brilliant and operationally impossible at the same time. A reminder that in railroading, as in life, it's not enough to be right. You have to be right in a way the world can actually use. What other stories are fading before we notice they're gone?